So what did we finish off with last time? We finished off solubility equilibria. Right, where we were determining if something precipitates or not in solution. Right, so we talked a couple things. The time before that, we mentioned something called the common ion effect. And so who can tell me what the common ion effect was? Or who remembers? In terms of solubility, precipitates of ionic compounds and stuff, what was the common ion effect? So we had something, I don't know, calcium carbonate, which is our solid, and that dissociates into calcium 2 plus, aqueous, CO3, 2 minus, aqueous, right? How would the common ion effect potentially affect the solubility of something like this? What might you add to this solution, or what could you potentially add to this solution to decrease the solubility of calcium carbonate in this, for example? If we decrease solubility, which direction do we shift this reaction? Left or right? You can point it. If we're decreasing solubility, are we putting stuff more in the aqueous phase or the solid phase? Solid phase, right? Because we want stuff to precipitate when we decrease the solubility, right? So what could we add to this solution to make things more in the solid phase? Which way should the equilibrium shift? To the left, right? It should shift to the left, right? Because we want stuff to either stay or go into the solid phase, right? So if we're trying to come up with something, right? According to the Chavalier's principle, we should do what to get stuff to move to the left, or the reaction to move to the left here? Add more product, right? So we should have something in there that adds more product here. And we don't necessarily have to add it after we put the calcium carbonate. We can already have that in solution, right? So we can already have some stuff in solution that then makes it less soluble, meaning that this equilibrium has shifted to the left. And so does anyone have an idea of something you could add?
More CO3.
Yeah, so something with a source of either carbonate or of calcium ions, right? So equilibrium constant for solubility, right? So that's KSP is just our regular equilibrium constant, except we don't have the, in this case, the solid there, because KSP is just equal to the concentrations of the ions here, right? So this is CO3, 2 minus. And if we add something that is a source of calcium or carbonate, then that could shift the equilibrium to the left, right? So we could add calcium oxide, for example, right? So all I'm doing is I'm just matching charges. Anything that carries 2 minus charges I can use. So I could do that. I could do calcium fluoride. If I had a salt of calcium fluoride, so CaF2, that would also shift the equilibrium. It would reduce the solubility of calcium carbonate. Or if I had, another metallic ion like magnesium carbonate or something like that. Those would also shift the equilibrium to the left for this reaction. When we shift our dissolution process, right, where we're dissolving some solid, right, we're just using equilibrium to understand this physical process of dissolving an ionic solid. When we shift it to the left, that's decreasing the solubility. That's the same thing. Okay, so then we have, we can explicitly calculate how does that affect the solubility, right? By using an ice table, we have some initial value now for this ion. If we have the other common ion present, right? That's why it's called the common ion effect, because if any of these salts are in solution, then these both have a common ion with our solubility product of interest. Right, so these are sources of common ions. Of common ions. Alrighty. So I know it was, almost a week ago last time we discussed this, but right, so this is the main idea here. And again, everything we're studying for this month is basically looking at equilibrium and how is it useful in these different scenarios. Right, so we had gas phase reactions, just regular aqueous reactions for equilibrium concentrations, and then we started talking about solubility. And so then we also could use the same line of reasoning to then determine if something precipitates in solution, right? So does something precipitate in solution? And this was if we had two salts that may be mixed together, like lead nitrate and we'll say calcium chloride, right? So if we mix these two salts in solution, we want to know, does PbCl2 form, right? This is another thing that we could use our solubility product and then determine. And so if we did that, or how would we approach this problem, right? If I gave you some amount of lead nitrate and some amount of calcium chloride, how would you ask, or how would you decide if lead chloride forms? What else would you need to be given here, right? So you're given some initial concentrations. Initial concentrations, and what else? Determine if lead chloride is going to precipitate, or lead 2 chloride is going to precipitate. If we're looking at lead 2 chloride forming, what's the equilibrium reaction for that? Or what's the dissolution reaction? Really?
Which one did you say was? Like,
Oh, lead 2 chloride. Like, so PbCl2, right? If we have, that is what I want to know. What's the dissociation or dissolving reaction for that? Right, what's the charge on each chlorine ion? -1, right, for an ionic compound. And what about on the lead? It's lead 2 chloride, so it should be 2+, right? +2. Right, so what's the dissolution reaction for lead 2 chloride? Right, our solid is PbCl2, right? When I ask the dissolution reaction, what goes on the product side here? Hmm? So the lead nitrate, right, if we have just lead chloride on this side of the reaction, and where it's a dissolving of this ionic solid, that means we can only end up with whatever's on this side of the reaction, right? these two compounds, right, these are our strong electrolytes in solution where these dissolve, completely, right? We get a dissociation completely of these two, and they just give us a source of lead ions and chlorine ions here. So that's the reason that we have to have both of these here, because they give us a source of lead and of chlorine ions, right? So for our actual dissolution reaction, we know that this is the solid that we're looking at, but what's on the product side here can only be ions that we get from this solid here. So what would be the 3 ions total that we would get? We get lead plus 2, aqueous, right? Because that's in the aqueous phase, that ion, and what else? 2 Cl minus, right? So our 2 ions, these are soluble in water, because ions are soluble in water because of the way water can move its partial positives and negatives around. And so this is our actual dissolution reaction. And we want to say if we mix a certain amount of these two together, does this precipitate, right? So if this precipitates, that means that the equilibrium shifts in which direction? To the left, right? For precipitate to form. Right, so it shifts to the left for the precipitate to form. So if you're given some initial concentrations, what else do you need to be able to determine which way the equilibrium will shift? What else do you think you need? If you have initial concentrations, right, what can you calculate that you can compare to what it is that I'm asking for? I know that was a lot of questions in one question, but.
The equilibrium?
We need the equilibrium constant, right? We need our solubility, right? We need KSP for this. And so how does the initial concentrations and KSP help us determine if this shifts left or right? Arhelia? If we have, so you're saying if we have PV or CL, so it will be related to the ratio of how much of each of these we have, right? But we can actually calculate qualitatively which direction this reaction will shift, right? How can we determine which way a reaction moves if we're given some initial concentrations before you mix them? Right, and this isn't just for the solubility product, this is for equilibrium in general. We compare KSP and we compare that to QSP, right? Where QSP is the same thing as KSP, just with some initial concentrations, right? KSP is our equilibrium related to our equilibrium concentration. So when we're mixing these two together at whatever concentration or amount that there is, we're saying, do we have enough, right, in the aqueous phase to start precipitating things into the solid phase, right? So if our ratio, let's say, so it's Cl or Pb 2 plus Cl minus squared. If our value of QSP is less than this, right? So it's less than the amount that we have at equilibrium, then we still need to make more aqueous ions before we shift things into the solid phase, right? It's the same way as when we look at our equilibrium constant and our, we compare the value of Q and KSP, except we have reactants and products. Here we only have products, but the interpretation is still the same. This value, right, for QSP, right, because QSP is the same thing. Pb 2 plus CO minus squared, except these are not at equilibrium, right? These are initial concentrations. Right, so if these are our initial concentrations, if this value is less than KSP, right, that means that we need to shift to make more of these to increase it. There's nothing that we can divide by in this case, right? Because the solid, how much solid you have there doesn't actually affect the direction of this equilibrium at all, right? That's why we don't include them in the equilibrium constant. So if QSP is greater than KSP, right? So if this is greater than, right? So one of the tricks you can, if you don't want to look at the ratios and compare the actual values, if you always put QSP on the right, whichever direction the arrow points in, that's the direction the reaction is going to shift, right? So if QSP is greater than KSP, right, the reaction is going to shift to the left, right? Because that means that we have too much aqueous stuff in solution, and we need to make some solid to reduce that concentration so that we reach the equilibrium concentrations. Right, so there's some critical concentration of these that we need before we start precipitating stuff out. Until we reach that, stuff is just going to stay in the aqueous phase. And so, I bring it up. I brought it up last week, but I'll say so. Daphne asked a question in office hours last week as well. We don't have any of this in our initial mixture, right? Does not mean that the reaction is always just going to move in that direction. It would if it wasn't a solid, right? Because it's a solid, it doesn't affect the position of the equilibrium at all. All that matters is the concentration of these products, whether you form the solid or not. So you could even have some of this solid already, not dissolved in the solution, mix these two things together, and it's only the concentration of these that you get from this, these two sources that shift the equilibrium one direction or the other. Right, so I know it's a lot to keep track of, right? But it's the same idea as with the gas phase reaction. The only thing is that we're just looking at something called the solubility product because we don't have anything in the denominator here. There's nothing on the reactant side of this reaction because it's a solid. All right. How do you guys feel about that? Thumbs up, thumbs to the side, or thumbs down? All right, I think we're making progress. We're getting there. We'll keep discussing it. I was gonna move on to acids and bases pretty fast today, but I think since I had the exam date wrong in my head, we'll discuss this for a little bit. Maybe after the break, we'll start talking about acids and bases. Okay, so let's go to an example of this, right? So why don't you guys spend some time, see if you can figure this out, right? So we have 4 liters of 5 molar, or 0.5 molar lead nitrate, lead nitrate, and 1.6 liters of 2.5 times 10 to the minus 2 molar sodium chloride, right? So this is exactly the problem that we were just looking at. Predict whether lead chloride will precipitate from the solution after mixing, right? You're given the KSP, or the equilibrium constant, for lead chloride. Right, so the first thing you want to do is write the dissolution reaction, and then you want to think about what concentrations you're given, and how do those relate to equilibrium concentrations, and how can you determine which direction the reaction is shifting. Do in this problem. Right, this problem just has one extra small step you have to do. Yeah, because we're mixing 2 different fluids of 2 different volumes, we have to calculate the new concentrations when we mix them together, right? So how do we get the new concentrations from, if we're given the volume and the concentration of them, the initial volume and concentration of them? There's 2 different ways you could do it if you wanted.
Could you just put it in like this moles per liter?
Yeah, you could do that. That's one way. That's the way that I would instinctually do it. You can do, if you have 0.4 liters of lead nitrate times 0.5 molar, and what are the units of molarity? Moles over liters, right? So this is PbNO3, 2, and PbNO3 I mentioned this last time, and I would tell you guys this if it was a problem. This is a strong electrolyte. And so what was a strong electrolyte again? All right, so this is, we're introducing this idea of, or allegedly, everyone should know this before they before they come here, but if your previous class didn't go over this, a strong electrolyte is going to be related to what a strong acid and base is. It basically just means that when we have an ionic solid, that it's going to dissociate 100%, right? So 100% of the time, we get our NO3 minus ions and lead-2 ions, right? So 100% of this is going to dissociate in a solution of water, right? It just means that the solubility of this compound in water is like 100%. The equilibrium constant is infinity because it all just goes to the aqueous phase, right? So when you're given a mixture like this, and the same thing with sodium chloride, right? We know sodium chloride is a strong electrolyte. When you put that in water, it dissolves right away. And so if we have then, this is moles per liter, 0.4 liters times this quantity molarity gives us the moles of lead nitrate, right? So this gives us 0.200 mole lead nitrate, and because it dissociates 100%, 1 mole of lead nitrate gives us 1 mole of lead ions, right? So the reason that we get this is because PbNO3, 2, solid, because it's a strong electrolyte, gives us Pb2 plus, aqueous plus 2, NO3 minus aqueous, right? This is the reaction for this dissolving, and for every 1 mole of this we dissolve, we get 1 mole of lead, right? So each mole, or so if we're given this concentration, that's the same concentration of lead ions we get in solution. Bless you. And so if we have the moles of lead ions in solution, right, initially, how do we use that to get our initial concentration? Right, what should be our new volume? The total volume, and the total volume is what? 2 liters, right? So we use this. This gives us a total volume of 2 liters, right? So our new concentration is just the moles of lead ions, which is equal to the moles of lead nitrate. And you could do a full unit conversion to get the moles, and I can do that if you guys want, just so you see why this is a 1-to-1 mole ratio. Divided by the new total volume gives us our initial concentration of lead ions. Right? So this would then give us 0.100 molarity of Pb2 plus, right? The other way you could do it is you can also use M1V1 equals M2V2, or you have your initial concentration of lead with 4 liters, and then you know your final volume is 2 liters. You just have to make sure you add the 2 volumes together because that's your total final volume, right? Everything is in aqueous solutions, right? Everything we deal with. We almost are never dealing with pure liquids of any type except water. And so we could do the same thing for sodium chloride, and sodium chloride is going to give us the concentration of what for our eventual reaction of interest? What's the other ion we want to find the concentration, or the initial concentration of? Chlorine, right? Because our solid is lead chloride, right? So we want to find the concentration of chlorine, right? So since we're looking for lead chloride, we need the concentration of lead and the concentration of our chlorine ions. And so we use the sodium chloride concentration to get that, right? So we have 0.025 moles NaCl per 1 liter times our new volume, our original volume, which is 1.6 liters. That gives us our moles of sodium chloride, which is 0.025 times 1.6, 0.04 moles of sodium chloride. And for sodium chloride, how are our moles of sodium chloride related to our moles of chlorine ions? Right, if we think about this is our first, ionic compound that we dissolved, right? It was a 1-to-1 mole ratio. What is it for sodium chloride? How does, for sodium chloride, it would be NaCl, solid. If we were dissolving a solid, what would be the two ions we get from that? And what would be their stoichiometric coefficient? It should be a 1-to-1 ratio, right? Because we get sodium plus chlorine minus, right? So we still get a 1-to-1 ratio. So our moles of sodium chloride is equal to both our moles of sodium and moles of chlorine in solution. And the way we could rationalize that is using that equation up there. We get 1 mole NaCl equals 1 mole of Cl minus. Right? All I did is I just used this conversion factor that goes from moles of the reactant side to moles of the product side of the reaction. Right? So that's the same thing you guys should be familiar with from Chem 1A. So now our moles of sodium chloride cancels out. We're just left with moles of chlorine. And what do we have to do with this moles to get our initial concentration?
Divide by the
Yep.
total volume.
Yeah, we divide it by the total volume, and that gives us our new concentration. So 1/2L is the same thing as just dividing it by 2L. We do that, and we get 0.02 molarity of chlorine minus. Right, so I just did this extra step here because I didn't do it here, just to illustrate why this gives me the moles of lead 2 when I use the lead 2 nitrate to do that. Right, so this step I just did in my head right there, but I just wanted to show this explicitly here. All right, so now I have these two initial concentrations, right? So how do I know if I'm going to form any of our solid lead 2 chloride? All right, so I'm just going to make the next page, but I'll go back and let you guys think about that. Write our reaction, PbCl2, solid. This is our dissolution reaction, right? This is the actual dissolving of or the solubilizing of lead 2 chloride. What goes on the product side of this reaction? Pb2 plus aqueous plus Cl minus 2 aqueous, right? This is our reaction that says, are we going to have lead ions in the aqueous phase, or are we going to precipitate this solid, right? And so we want to calculate QSP, which is equal to the concentration of Pb2 plus Cl minus squared, and these are the initial concentrations, and then we want to compare that to KSP. So the two concentrations we just calculated were 1 molar times 0.02 molar squared. Right, so we just have to make sure we're keeping track of the squares from the coefficients here, and we can get QSP. And so we get 0.02 squared times 0.1. We get that this is equal to 1, 2, 3, 4, 5. 4 times 10 to the minus 5. All right, that's our value for QSP. 1.17 times 10 to the minus 5. And our equilibrium constant was 1.17 times 10 to the minus 5. So which one is larger and which one is smaller here?
QSP is larger.
QSP is larger. So if QSP is larger, right? Again, we can put QSP on the left. Which way does the little thing go on Q? This way, right? Yeah. KSP on the left, QSP on the right, in the direction of the greater than sign or equal, greater than or less than sign, which will tell us which way the reaction is going to move, right? And we're looking at this reaction right here. So if QSP is larger, which direction does the reaction shift?
Towards QSP.
It shifts towards the left, right? So do you guys think then a precipitate is going to form?
Yes.
Yeah, precipitate should be forming, right, because we're shifting the reaction towards the solid phase here, the solid reactants, right? Which means that this will precipitate will form. Right, it means that from our strong electrolytes, which give us chlorine ions and lead ions in solution, right, we get enough of them in solution to then move the equilibrium to the left, right? We've reached the critical concentration, right, where we've saturated the solution, and now we're moving it so that it becomes from a supersaturated solution to a saturated solution, right? The equilibrium point is exactly when we have the maximum amount dissolved that we can in the solution. Right, so pretty much once you have these initial concentrations, this is everything that's related to equilibrium, right? This whole first step was just set up for the problem, right? Calculating these concentrations is just set up, right? We have to recognize a couple things. We have to recognize that, and I would tell you this if it was a problem that I was writing, that lead nitrate and sodium chloride are strong electrolytes. Why do you need that information? Well, that tells you that the concentration of your initial ionic compounds is equal to the concentration of those ions. And why do you need those ions? Well, you have to realize that these are the ions that are important for the precipitation of the solid that we're looking at. Right, so this is just set up, and that's the understanding we need to then be able to set up the problem. This is just from our first chemistry class, getting the new concentration when we mix two volumes together. That's just something like an extra step to give you in the problem. Once you have those concentrations, this is really all the math or all the work that's involved in the problem, right? We just calculate QSP, and we just compare that value to KSP to then determine which direction the reaction shifts. Right? The way this reaction shifts tells us, are we going to be in the aqueous phase or the solid phase? Right? If we shift to the left, well, that means we're making solid. If we shift to the right, then that means we're not going to precipitate any solid. We haven't reached a critical concentration to actually get the solid to form in solution yet. All right, any questions on that? No questions? Does anyone have a comment about what's confusing about setting up a problem like that?
Would there be one where the precipitate won't form at all?
Yeah, so if for example, let's say this came out to be 0 or 4 times 10 to the minus 6 or something, right? That means now that QSP is less than KSP. So the reaction is going to be shifting to the right. And so if this shifts to the right, that means we keep everything in the aqueous phase, right? So in that case, precipitate won't form, right? We're not at that critical concentration where we've saturated the solution and we start forming a solid. So this is if we remember what KSP and QSP and their relationship to each other means, that'll tell us what the precipitate forms, right? Everything else is just setting it up so that we can calculate what QSP is. But yeah, I could give you one that where it won't form. It potentially couldn't form. I think last time we did one where it didn't form is where we ended off with this one, I think. All right, these were actually a little more challenging when we were solving for the minimum concentration, right? Because then we had to realize, oh, the minimum concentration is right when we're at equilibrium, when QSP and KSP are equal to each other. All right, so those would be good to review too. Okay. How are you feeling now after this problem? Thumbs up, thumbs to the side, or about a problem like this? Or thumbs down? Okay, so we'll keep practicing this, and also on the problem set, you guys have one like this too. And then the makeup quiz will also have, you know, some problems like this. So even if you do really well on the quiz, you know, still look at the makeup quiz for study material. Another thing you can look for questions is a lot of times I'll leave certain questions unanswered in the notes. So you can always go through those and do the unanswered questions. Or what you can do is, I always publish the uncompleted version of the notes, is you can go through those and see if you can answer the questions we do in lecture, right? So question 3 on the quiz last time was exactly the same question that we did in the lecture itself. Question? Do you have a question? Oh, okay. Right, so that was the exact same question. So sometimes I'll pull stuff like that just to, you know, say, oh, make sure you go over questions like these in the notes. Okay, all right, so that was part of where we ended with last time. And the last thing that we talked about in lab was for using equilibrium to understand complex ion formation, right? So now we're not looking at stuff that's solid and aqueous, right? Because everything in the complex ion is aqueous, right? Because it's a complex ion, that means it's a charged compound. Usually those are going to be very, very soluble in water, right? So let's see if I'll use this example right here. We have Hg 2 plus, which is aqueous, plus, what is it, 4? Oops. 4 I minus aqueous goes to Hg I4 2 minus, I believe is what it goes to, right? Hg2 minus, yeah. So this is the formation of our complex ion, right? It's a complex ion because it's a molecule or a coordination compound that then has a charge on it, which is why it's also aqueous, it's in solution. And so unlike solids, which tend to be, you know, their equilibrium constants tend to be very, very small, right? Because we don't dissolve a whole lot in solution. We had an equilibrium constant, which was called Kf. And Kf, does anyone remember what it was called? What does the F stand for in Kf? The formation constant, right? It's the same thing as any equilibrium constant we looked at, except now we're just specifying that this is for a complex ion formation, right? So this is Kf, and what would Kf be for this reaction?
Would it just be equal to Hg, or the concentration of it?
It would be Hg I4 2 minus concentration, right? And do we include the ions here?
Yeah, they're aqueous.
Yeah, because they're aqueous, right? So we're always thinking, what states of matter are we dealing with in our equilibrium? Why? Because liquids, solids don't affect the equilibrium at all, right? So then we include Hg 2 plus, and then I minus to the power of 4, right? So when I see stoichiometric coefficient like 4, there was also something that we did to simplify these problems. We know if we're looking at an ice table for this, power of 4 is going to be hard to solve for a polynomial, right? So we have to think about, okay, how might this problem solve, right? So this is our equilibrium constant, except now instead of looking at a gas phase reaction, a regular aqueous reaction, or solubility of something, we're looking at the formation of a complex ion, right? So same idea, we're just using equilibrium to understand how these concentrations are affected for this complex ion. In Kf, these values, they tended to be very large, right? Which means that if this value is large, we're talking like power 10 to the 30, 10 to the 20, something like that. That means what's favored at equilibrium? The products are favored, right? If Kf is large, and this is our ratio concentration. That means that the numerator is very, very large compared to the denominator, right? That means that products are favored at equilibrium. All right, which is the same thing if I asked you, well, I gave you a random reaction, I said, okay, the equilibrium constant is large, and you would, that's how you would normally approach that. Well, it's larger than 1, a lot larger than 1, so that means that products have to be favored. And so looking at, does anyone remember, you know, why in our qualitative analysis or in other labs we have used complex ions, right? Why might we use complex ions, or how might they be used in a lab setting? Let's say we had this other reaction. HgCl2 solid Hg 2 plus aqueous plus Cl minus aqueous. If we have this other reaction going on in our solution, what does this reaction potentially do to that first reaction? Or how could we describe this process in a lab setting? Specifically, what does it do to that compound, right?
Reduces the amount of it.
Do you say reduce it? Yeah, it reduces the amount of it, right? Because if we know that the formation of these tend to be very, very large, right? Which direction is this reaction going to shift in? If you're out of equilibrium. If you're going to form this, and let's say you don't have much of it, the reaction shifts which way? Right or left? Right, right? If this is very favorable to form, that means you want to make as much of the complex ion as possible. And if you're doing that, what are you doing to the concentration of this ion here? You're decreasing it, right? And that's also in this reaction here, right? So if you're decreasing this, what are you doing to the concentration in this reaction as well? Decreasing it as well, right? So if you're decreasing the concentration of this product here, which way is this reaction up top going to shift? To the right, right? If you're decreasing the concentration of a product, that means that the reaction is going to shift to counteract that change. It's going to start making more of this. And so what it does is originally we have solid, and let's say it's not very soluble in our solution. You have this other complex ion formation reaction going on. Now all of a sudden you largely increase the solubility of this compound because you're forcing it to go into the aqueous phase, right? Because we have a kind of chain reaction of Le Chatelier's principle, right? This is going to be forming, which decreases the concentration of this, which then decreases, this is the same thing, so that concentration is decreasing. The Chatelier's principle say we need to make more of that to compensate, right? So you're going to increase the solubility of that. And if you wanted to, you could actually go through and calculate how that affects the solubility of that by looking at the new equilibrium reaction, right? So if you did that, that means that you have two different equilibrium constants, and you add the two reactions together, and that'll give you the new solubility of that compound. We'll talk about that maybe more in our problem set for this upcoming week. But these can be used to increase the solubility of some solids, some relatively insoluble solids that we have in solution. The formation of the complex ion is super favorable, so it decreases the concentration of some ions in solution, which means that it'll force other things to dissolve in solution when that happens. And so again, I mentioned it in the lab, but keep in mind when you're doing the qualitative analysis lab, why am I adding this to solution? Is there a complex ion that's going to be forming that's then making the solid soluble, where in the previous case it wasn't? And so we talked and went over one example where we looked at calculating equilibrium concentrations given initial concentrations and the formation constant for a complex ion, right? So we then used our principles of equilibrium to calculate equilibrium concentrations given initial concentrations and Kf, right? So these are the two things that we need to solve for equilibrium concentrations, which is really the two things that we've needed for all of our equilibrium problems, right? If we're ever looking for the equilibrium concentration, we need initial concentrations and the equilibrium constant for that process. And what was the tool that we used to do that? How do we calculate equilibrium concentrations? Ice tables, right? So we use ice tables, right? This is where we use ice tables. So we use the ice tables, given some initial. We set some arbitrary change, use that arbitrary change to give us our equilibrium concentrations, and then relate those to the equilibrium constant. And that's where we might have to use small x approximation or quadratic formula, or that's where our math is involved in solving for that x value. And then for our formation constants, there was one extra little trick that we had to do for that. Right? Does anyone remember what the trick that we had to do for the formation constant was? And it's related to because these values are so large is why we do this trick.
Small x approximation.
We want to use a small x approximation. So a lot of times these complex ion formations have these really large stoichiometric coefficients. And solving a polynomial like that is really annoying. So we're probably going to have to use a small x approximation. But the method we used was, if anyone remembers, it's called the bounce back method, where you assume all of the complex ion forms, and then a little bit goes back for the change, right? So there's one extra step in solving for the initial concentrations. It's saying that it's equivalent to assume that all of this forms, and then we're assuming a little bit goes back the other way. And so, the reason that you do that is because if we know this is going to be large, then any change going back in the other direction is going to be small, and that'll allow us to simplify these problems. There are other equivalent ways to do that. For example, you could flip this reaction around and do the same thing. If you flip this reaction around, what do you have to do for the equilibrium constant? Right, if you're given Kf and then you reverse the reaction, what's the new equilibrium constant related to Kf? Yep, it would be 1 over Kf, right? So if this is very large, if Kf is very large, then 1 over that would be very small. So the reverse reaction has very little that goes in that direction. And so that's why you can flip this reaction around and you would get the equivalent answer. Both of these, doing it either way, is the same thing. The reason we use the bounce back method is just because then we don't have to flip any reactions around. And so I'm just going to go back to the previous problem I'll let you guys look at that. But the previous problem that we did in regards to that, where we actually calculated the initial concentrations using that. So when we looked at this complex ion formation, right, we assumed that all the reactants combine to form the complex, right? So we're given a source of these ions in solution. The initial step is to assume that you make all the complex ion here, right? So I start off with this much of ammonia, this much of copper. I use as much as I can to then make my complex ion, right? So I lose both of these, keeping account of stoichiometric coefficients. And that gives me the initial concentrations, assuming that I made everything I could for the complex ion. And then I use these values as my initial values for my ice table, right? So those values now go up here, and I'm assuming that the reaction is going in the other direction, right? So I start with this, I'm losing my product here, and I'm adding to my reactants. And now because I know the Kf is very, very large, if I start off with some amount of this, it's gonna be very unfavorable to go back in the other direction, right? Because that's what we said, right? We said that this is very favored at equilibrium. So I should only go back a little bit. When I only go back a little bit, now I can assume that things that are added to these numbers are gonna be very small, right? This change on the way to equilibrium is gonna be extremely small, and I can use the small x approximation to then simplify this polynomial, right? Because if we have something to the fourth power, or third power, or any other power that's not 2, that should immediately signify, okay, I have to simplify this problem somehow. And so then we just went through a bunch of math to then solve that. We didn't actually solve for this problem. So why don't we take the next 10 minutes and see if you guys can set that up for the complex ion formation that we just, the reaction that we just looked at for the review page, right? So here you're given a value for the formation constant, which is just equilibrium constant for this reaction. It's a very, very large value, right? And after complexation, you have this original concentration of your ions. Again, the first step is going to be to calculate your initial concentrations, assuming that you form all of the product here, right? So first step, assume all product is formed. So you can set up a table to do that if you want. And then the second step is to set up an ice table to solve for x. Methodology for this was called the bounce back method. Okay, so let's set up our initial concentrations first, right? We have H2 plus, mercury, 4I minus, and then HgI4, 2 minus. So we start off with 0.01 molar of this, 0.78 molar of this, and 0 of our complex ion. We assume that all of our complex ion forms, right? Which means that one of our reactants is going to be the limiting reactant, and that determines how much of our complex ion we're going to start off with, right? So which one do you think is going to be the limiting reactant in this case?
HG.
It should be Hg, right? Because how can I do that just without going through all the calculations? Well, 4 times this value is still less than that, and this is a 1-to-1 ratio there, and for every 4 of these, we make one of those, right? So 4 times this is still less than that, then this is what's going to limit the reaction. Generally, it'll be pretty obvious because one of the concentrations are much smaller than the other. So this will be minus 0.01 molar because it's our limiting reactant. This will be minus 0.01 molar times 4, right? Because we have a stoichiometric coefficient of 4. And this will be plus 0.01 molar, right? And so we do that and we get 0.77 molar, and 0.01 molar, right? So these are our new initial concentrations, right? This is the bounce back method. First we make all of our complex ion, and then we set up the ice table that goes back in the other direction. All right, so that's what, if you haven't gotten to that part yet, now you can work and set up the ice table. These should be our initial concentrations.
Wait, why is it 0.77 instead of
Oh.
0.74?
0.70, oh yeah, you're right, because I forgot the 4. Yep, good catch, because it's times 4. 74. So all I did was I just added these 2 rows to get that answer. So our new ice table, initial change, equilibrium, we have 0, 0.74 molar, and 0.01 molar, right? This is, again, this is, we're simplifying, calling the bounce back method. So which way is the reaction going to go at this point? What are we going to assume that it's going? Right, these are our initial concentrations we're starting off with, right? We have 0 of this product right here, right? So technically that means that the Q would be undefined blows up to infinity, or negative, not negative infinity. It blows up because we're dividing by 0, but because we have 0, that means we're gonna move the direction, the reaction in that direction. So that means that our change is gonna take that into account, right? So if our change, if we're moving the reaction to the left, right, this is our reaction moving towards that, what's the change gonna be for these two? Positive or negative? Positive, right? Because we're making reactants in this case. Again, the direction of the reaction gives us the sign of the change. And what about for the mercury complex ion? Negative, right? So this should be negative. And this will be minus x for this because we have a stoichiometric coefficient of 1. What should it be for the iodine ion, the iodide ion?
4.
Plus 4x. And then for mercury, plus x, right? So then our equilibrium values are 0.74 plus 4x, and then 0.01 minus x, right? So these are our equilibrium concentrations. And so those go where? How do we use the equilibrium concentrations, right? We eventually want to solve for what x is, right? Because the value of x gives us these equilibrium concentrations, right? But here we've solved for them in terms of x. So how do we use these concentrations here? Right, what do we have a relationship between those concentrations and what else? Kf, right? Our Kf is equal to Hg(I4) 2 minus over Hg 2 plus and I4 or I minus to the power of 4, right? So we plug those values into here, right? Because those are what those expressions represent. They represent those concentrations at equilibrium. So this equals 0.01 minus x over x times 0.74 plus 4x to the 4th power. Since Kf is very large, right, it's extremely large, it's 10 to the power of 30, and we're talking about equilibrium moving back towards the reactants. Kf being large implies what's favored at equilibrium? Products are favored at equilibrium. And if the products are favored at equilibrium, if we're moving to form reactants, how should the value of x compare to this value right here, right? If this is something like 10 to the 30, right? That's huge. It's products are super favored, right? So this change should be what? The change forming the reactants, right? Because we're going back in the other direction, right? Bounce back methods, moving back in the direction. If we initially formed all of everything formed into the products, right? That was our first step. And now we're going back in the other direction. But we know products are very, very favored at equilibrium. How much should we create of the reactants? Should it be a lot or a little? Very small amount, right? Very, very small amount. Because if this is something like 10 to the 30, then going back in the other direction is like 10 to the minus 30, right? It should be something around that order of magnitude. So that means that our change going back in the other direction is going to be a concentration change of like 10 to the minus 30 or 10 to the minus 20. Should be small, right? And this change, right, that's what x is, right? This change of forming reactants is what x is. That's a change on the way to equilibrium. And so, when we add or subtract something small from something much larger, the number doesn't change much. Right, if we have 1.00 minus 0.000001, that equals 0.999999, and that's basically just equal to 1.00, right? If we subtract or add something very, very small, it does not change that number hardly at all, right? So this is what allows us to make the small x approximation, right? This is the small x approximation. So since this doesn't hardly change the number at all, it allows us to then simplify this expression, right? Because this is being added to something much larger, and this is being subtracted to something much larger. I'll give you guys a second to finish writing, and then we'll take a break. Oops. All right, this is what we're doing when we're assuming that x is small here. And so applying this to our problem means that 0.01 minus x is approximately equal to 0.01, and 0.74 plus 4x is approximately equal to 0.74. So our expression, kf, goes to 0.01 over x times 0.74 to the fourth power. So the reason that we can't get rid of this x here is because whether x is small or large doesn't change anything here because it's multiplied into anything else. If you're multiplying something by something small or large, you can't get rid of this because that affects the size of this number, right? We can do this because they're added and subtracted to each other. That doesn't change this number very much. But something large or small multiplied to this number changes that number a lot, right? So we only do this when we're adding or subtracting numbers together. So if that equals kf, then we can just multiply both sides by x. And divide both sides by kf to isolate x. That gets rid of kf on this side and gets rid of x on the other side. We get 0.01 over kf 0.4 to the fourth power equals x. And then we would just get our equilibrium concentrations by just plugging in x to our expressions that we had before. Right, and so you can see right now that x is going to be extremely, extremely small, right? Because, I forgot the f there. Right, we're dividing 0.1 by something like 10 to the 30. Right, so you can go back and calculate x, and you'll see that the equilibrium concentrations aren't going to be that far off of what we started with. All right, so this is the bounce back method, and this is for looking at complex ion formation, which is almost the opposite of dissolution, right? Because those values tend to be very small, these tend to be very, very large. The principles in setting up the ice tables is the same. Here we just have to do one extra step to simplify the math a little farther down. You don't have to do the bounce back method, but it would make it very complicated to solve because you couldn't use the small x approximation if you didn't use the bounce back method. All right, so let's take like a 12-minute break. So we'll be back at 10:10. And then we'll continue with acids and bases.